Hello students, in this video we will do the proof of Leibniz rule, and you know that Leibniz theorem or Leibniz rule is used to find the derivative of any integral. So if you are given with any question to find the derivative of integral, you can use the Leibniz rule. So in this video we will do the proof of Leibniz rule, and in the next video we will do some example, the practical example of applying the Leibniz rule on any integral for finding the derivative. So let's discuss first of all the statement of Leibniz rule. Leibniz rule is basically the differentiation of any integral. Let f of xt and partial f or partial t be continuous in the domain of xt plane. Like you have here two planes. The one of the plane is t plane and the other plane is x plane. You have to take the domain of x between a and b. Like for example, this is the a and this is b. Make the complete lines because we have the equality here as well. And the t is bounded between t and t naught. Like for example, t naught and t1. For example, this is t1 and this is t naught. Then within this region, this function f of xt and its derivative with respect to t must be continuous. If capital F of x equal integration from alpha of x to the beta of x f of xt dt, then how we can find its derivative? Apply the derivative on both sides like this. Then this will become your f dash of x. So derivative of that integral is going to be integration from alpha of x to the beta of x. Find the derivative of this your inner function with respect to x dt. Plus, now whatever your integral function is, the integrand is, you have to replace your t. You are finding the integration with respect to t. So you have to replace your t first of all with the upper limit of integration and derivative of upper limit of integration with respect to x. Minus, replace this t with the lower limit of integration f of x alpha and find this lower limit integration with respect to x. Find its derivative with respect to x. So this is your statement of Leibniz rule. Like if you're finding the derivative of any integral, find the derivative of inside function, then replace this function y or the second coordinate with the upper limit and find the derivative of upper limit with respect to x, minus replace your function second coordinate with the lower limit and the derivative of this lower limit with respect to x. Now we're going to find how we can prove this. Let's prove this Leibniz rule now. Now to prove this Leibniz rule, you have to consider your left hand side. In your left hand side, consider this integral equals to some other function, like I am letting here it equals to phi. Now phi is depending upon which variables? You can see here we have here which variables? We have here x variable, we have here beta, we have here alpha. So let's take the phi as x alpha beta. Phi is a function of these three, equals to this integral alpha of x, beta of x, capital F of xy dy. I just took this integral equals to some other function. Now mark it as equation number 1. We know that from the fundamental theorem of calculus, we know that integration of capital F of xy dy is small f of xy, and this partial f over partial y is capital F of xy. This is the fundamental theorem of calculus. Mark it as equation number 2. Now, from equation number 1 and equation number 2, you can write it, this capital F of xy is now partial f over partial y. So, from 1 and 2, what we can write? We can write it as phi of x alpha beta equal integration from alpha of x to the beta of x. Now this capital F of xy is partial f over partial y dy. Now you know that they're going to cancel each other's effect, and what we are left with, we are just left with our function f and the limits of integration. So your y, it's the integration with respect to y, so you are going to replace your y with the upper limit and the lower limit. So f of x beta minus f of x alpha. So what do you got as your phi? Your phi is now f of x beta minus f of x alpha. Now let's take its derivative with respect to, first of all, alpha, and then I will take its derivative with respect to beta. So first of all, let's take its derivative with respect to alpha. So partial phi over partial alpha equal, first of all, its derivative with respect to alpha, partial by partial alpha of this f of x beta minus partial over partial alpha of f of x alpha. Now you can see that this is a function of x and beta only. So its derivative with respect to alpha is going to be 0. So you got here partial phi over partial alpha equal minus partial f of x alpha over partial phi alpha. And you know that that is basically equals to negative capital F of x alpha by a fundamental theorem of calculus. Now, let's move on. Now we know that from our equation number 2, the equation number 2, we wrote it as partial f over partial y is capital F of xy. So let's use this. From equation 2, we had partial f over partial y was capital F of xy. Now if we replace this y with the alpha, we can write it partial f over partial alpha is capital F x of alpha. And you know that this capital F of x alpha was partial phi over partial alpha, negative partial phi over partial alpha. So what you can write, you know that partial phi over partial alpha was negative f of x alpha. So mark it as equation number 3. Now first I just took this derivative of phi with respect to alpha, this one that we did here. Now I'm finding this phi derivative with respect to beta. So let's find its derivative with respect to beta. So partial phi over partial beta, its derivative with respect to beta. So that is partial over partial beta f of x beta minus partial over partial beta of f of x beta. Now you know that f of this was alpha. Now you know that there is this f is not a function of beta, so its derivative with respect to beta is going to be 0. So what we are left with? We are just left with here partial phi over partial beta equal only this function, partial f over partial beta. And you know that that is capital F of x beta. Mark it as equation number 4. Now what you let in the start, you let in the start this thing, phi. So let's write it again. You had phi was integration from alpha of x to beta of x f of x by dy. What you need in your question, d by dx. you need in your question d by dx. Okay, so you need for your question d phi over dx. Let's write it on another page. In your question you have d phi over dx from your phi. Now you know that your phi is a function of three variables. Your phi is a function of three variables. So you're going to use the chain rule here. So d phi over dx is going to be partial phi over partial x over partial x, plus partial phi over partial alpha over partial x, plus partial phi over partial beta over partial x. So this is going to be 1. So you're just left with partial phi over partial x plus partial phi over partial alpha over partial x plus partial phi over partial beta over partial x. Now we need to plug in here the values, all the values. So this is d by dx as it is, d by dx, and your phi was in your question integration from alpha of x to the beta of x, f of x by dy equal. What was your partial phi over partial x? We need its value, partial phi over partial x, and that is just partial phi over partial x. So it's going to be integration from alpha of x, beta of x, and that's partial f over partial x dy. Let's use it. So that's integration from alpha of x, beta of x, partial f over partial x dy, plus now your partial phi over partial alpha. Your partial phi over partial alpha, what was that? Partial phi over partial alpha was minus f of x alpha. So let's use its value. It's positive times this minus is going to be minus here, f of x alpha, and this is partial alpha over partial x. Now what was your partial phi over partial beta? Your partial phi over partial beta was f of x beta. So plus f of x beta and partial beta over partial x as it is. So this is the same Leibniz rule you wanted to prove here. So we can use this Leibniz rule for finding the derivative of an integral. But there is some limitation of this Leibniz rule. We cannot use this Leibniz rule for the Abel's singular integral equation. We cannot use Leibniz rule for Abel's singular integral equation. And what is this Abel's integral equation? Integral equation of this form. F of x is integration from 0 to x u of t divided by x minus t raised to power alpha dt, where 0 is less than alpha is less than 1. You know that if we just plug in here in place of t the x, it's going to be undefined. So that's why it's Abel's singular integral equation. We cannot use this rule here for the Abel's singular integral equation, else we can use it for any integral equation. I hope you understand this proof. In the next video we are going to do some examples that how we are going to apply this Leibniz rule.